Hello, everyone, welcome back to Level Up Diary. I am Angeline. In this video, we'll implement and optimize a PID controller in Simulink for an AC to DC converter, using an EL and group optimization (EGO) algorithm to automatically find the best controller gains. Here is the implementation overview. Step 1 is to implement the AC to DC converter. Step 2 is to model the PID controller parameters. Step 3 is to implement the optimization algorithm in MATLAB. Step 4 is to run the Simulink model. Step 5 is to analyze the results. First, let's model the AC to DC converter. This is a simple PFC boost converter circuit. It has two switches S1 and S2. These switches receive the control signal from PID controller. The input supply voltage is 325 volt at 50 Hz. The load here is AR load at a resistance of 50 ohm. Now, let's move to step 2. The PID controller implementation. This is the controller subsystem. There are 3 gains in the PID controller. They are named as KP, KI, and KD. These gain parameters will be optimally attained from the EGO algorithm. Previously, I have mentioned the AC supply voltage is also 325 volt. The goal is to maintain 350 DC voltage. Here the reference voltage is set as 350. The reference voltage is compared to the actual output voltage and the error signal is fed to the PID controller. The PID output determines the current reference or modulation signal for the switches. This signal tells the system how much current is needed to maintain the DC bus at 350 volt. Here the ISE error of our controller is also estimated and is loaded to workspace using to workspace block. This is going to be our objective value for the fitness function of our algorithm. The input voltage Vin is passed through a block called frec WT through sine block. This produces a pure sine wave in sync with the AC voltage. The sine wave defines the shape of the desired input current. Now, this sine wave is multiplied by the amplitude coming from the PID output. So, this gives you a sinusoidal current reference, IREF, that matches the AC input frequency and phase. Meaning, this is the ideal input current you want your converter to draw. Both Vin and In are taken as absolute values. The block Vin equals 0 checks whether the current AC half cycle is positive or negative. This is important because your converter switches S1 and S2 operate alternately. S1 controls current in the positive half cycle. S2 controls current in the negative half cycle. So this logic ensures that current always flows in the correct direction through the converter. Then this is the main code. Here we have initialized all the algorithm parameters and the algorithm is called in the line 14. A detailed explanation of the algorithm will be shared as a part 2 video. If you are still here and found this video useful, please hit subscribe. I have also uploaded the full Simulink model on my GitHub profile. Link is given in the description. Here now I am sharing the screenshots of the code. This is the objective function. Using a signin function we randomly assign KP, KD, and KI values as gain for the controller from the algorithm, and with that values the simulation runs and the IDE error of the control is checked, and this process is repeated for n number of iterations, and the assigned gain value with minimum error is chosen as the best gain and is assigned to the controller. This is the initialization function. This is the EGO algorithm. If you are new to optimization algorithms, this is just a new algorithm similar to particle swarm optimization. These are the outputs. This is the output voltage, which is DC. As we saw previously, we set our desired voltage as 350 volt and we have attained that. This is our input voltage and current, which are AC and is in phase. This is the convergence curve of the algorithm. Thanks for watching. The entire Simulink model is available on my GitHub site. For any doubts or Simulink implementation, contact me via the mail ID given in the description. Let me your doubts in the comments.